Good morning, everyone, and welcome to our session 5, I believe we are on with the Odell and AMCA education series. I am going into slideshow mode here for you. Today's topic is fan types in selection and fan maintenance. And as I have been with you for the series, I am Lisa Cherney, the Education Manager with AMCA International. I'll be moderating today's session. The very quick guidelines that we go through at the beginning of each session, the audience is muted. If you have questions for our presenter, please know that you can submit them anytime during this broadcast through the Q&A option on your control panel. We will get to those in about the last 10 minutes of today's session. We are recording this session, and the recording plus the PDF version of the slides will be posted on the Odell website within 48 hours. If you are interested in earning PDH credit for today, please do stay with us for the entire program. That is a requirement. And also as a requirement, complete the survey that we will send to you 1 hour after the conclusion of today's program. And even if you're not in this for PDH credit, we welcome you to complete that survey as well. Your feedback is very important to us. So once again, for Q&A, you will use the panel on the right side of your screen, select the Q&A option, type your question in, click send, and you can submit at any time. But remember that all attendees can see the questions that are submitted. So just keeping your self in check with language and such. If you happen to have a question that's a little too complicated or involved to type out, feel free to raise your hand. During the Q&A segment, there is a raise hand icon on your control panel, and we will unmute you and you can ask your question verbally. As usual, we do have to mention that AMCA has met the standards and requirements of RCEP, through which we are offering PDH credit for today's program. RCEP does not endorse any content or approve any content presented today. A brief disclaimer that the information we are providing is an educational service only and not intended to serve as professional engineering or manufacturing advice. We do ask that you note that the information presented today and the views are those of the presenter and do not necessarily represent the views of AMCA International. In making the activity available to the audience, we are not endorsing, sponsoring, or recommending any particular company, product, or application, and under no circumstances, including negligence, shall AMCA be liable for any damages arising out of a party's reliance upon or use of the content contained in today's program. The program is copyrighted by AMCA International, so any reproduction, distribution, or use of the materials without written permission is prohibited. So I would like to introduce you all to our presenter for today. Mike Human is the Manager of Products and Applications for the New York Blower Company. Mike has a Bachelor of Science degree with a concentration in physics from Elmhurst College, which is here in Illinois. He has over 10 years of experience working with industrial fans and in the fan industry, and he's given multiple presentations about fan applications, custom fan modifications, and fan system effect at various conferences and in many training sessions. So with that, I would like to turn the presentation over to Mike. Mike, I will stop sharing my screen and you can take it from here.
Thanks, Lisa. Welcome and good morning to everyone. Thanks for joining us. Hopefully everybody's doing well out there. So we'll review kind of the purpose and some learning objectives for the PDH credit here. So here we're just going to talk really kind of try to detail some of the requirements for proper fan selection and maintenance, including, at the end of this presentation, hopefully you'll be able to understand fan selection requirements better, also identify various fan types and their characteristics, and develop an understanding of basic fan maintenance. So when we talk about fan selection considerations, a couple of these items are really requirements, and the rest are considerations that can help you better identify certain things for your application and kind of help us help the fan selector make a better selection for the best selection for your fan application. The two real requirements of any fan selection are going to be flow and pressure, your capacities. Also, the other one is airstream density and airstream makeup. These two are really critical to any basic fan selection. The rest of these items really just kind of enhance or can better help us select the best fan for that application. Some of the other considerations, if you're looking for a belt or a direct drive fan, also if you have a specific fan arrangement in mind, any specific mounting requirements depending on the site or the application. You also have noise and vibration concerns. If there's a specification for that, certainly something you'd want to know ahead of time to provide the best fan for that, because some fans are just inherently louder than others. So that's something we definitely want to know up front. Also, how you're going to control the flow of your fan. Is it going to be VFD controlled? Are you going to control it via dampers? And the last two really are physical limitations. That's more about the site and the envelope the fan's trying to fit in. And last is cost, and that's really critical because you definitely have that initial capital cost. And an initial capital cost on one fan versus the next can be drastically different depending on some of the other requirements. Are you looking for the most efficient fan? That's going to typically be a little bit more. It's going to be more expensive than a fan that's not as efficient. There's certain techniques you can take for fans to be more efficient, and also just base designs. Certain fans are more expensive than others to manufacture, and included in that is, if you may have a large upfront cost for a more efficient fan, you're going to save on the back end of operating costs versus a less efficient fan. And also some considerations are taken into account for maintenance. And that's critical because if you want the fan to be as simple as possible to meet your application, so you don't have as many items to maintain if that's allowed in or works in that application. So when we talk about capacities, we kind of talked about flow and pressure. The flow rate, we're just basically calculated on the system requirements. And when we select a fan, we're looking for the ACFM required at the fan inlet. And same thing for pressure. If that's based on system static pressure requirements, the requirement of to move a volume through a system gives us a resistance, and that resistance is expressed in static pressure. And typically you see fan static pressure, fan total pressure. You'll see this expressed typically in imperial units, in inches water gauge, and in metric units you would see millimeters water gauge or pascals. Anytime we need to make a density correction, when the airstream is not standard, whether there's elevation or temperature involved, that's something we need to make a correction for when we're selecting a fan based on ACFM. So some other considerations, we certainly want to talk about airstream makeup, and that's critical to help select the best fan, and also the fan that's going to be able to handle the application and have some longevity versus incorrectly selecting a fan where you could have some potential issues. A couple of those, is the application clean or dirty? What is the airstream handling? Is there particulate in the airstream? Is it just clean, ambient air? That's certainly going to change the direction of your fan selection. Also, is there any explosive or flammable materials or gases involved? That'll be critical because we'll need to know if we need to offer some sort of spark resistance construction or maybe some other considerations to have that fan be able to handle those materials. The same goes for corrosives. If there is corrosives, we kind of like to you want to know that ahead of time, so we select the right type of fan, but also the right material to handle those corrosives. And last is really airstream temperature, and that's really critical, for proper selection of materials, but also proper selection of your fan arrangement and type. Kind of further expound on material handling. The first couple things, you really want to know if there's smoke and dust. You're going to be looking at certain types of fans. Those typically would be a backward inclined centrifugal or even an axial fan. And when you start to get to light dust, fumes, or moisture, you're going to want to look at, you can also look at a backward incline, but you're also going to, radials are going to start to creep in there as well as being, as working well in those applications. And that's really going to be application dependent, which way you can go, depending on what is being handled and what type of fan we can offer. And the last is once you get to high particulate loading and even material handling, where we're actually moving material through the fan, you're going to want to look at a radial fan at that point. So we talk about drive arrangements. The first arrangement we'll look at are direct drive fans. So you see here on the right-hand side of the screen, you see some examples of fans. The top picture is an arrangement 8 fan. You can see that the motor is coupled directly through a coupling into the fan shaft, and you'll have a set of bearings for the fan shaft, and then the impeller will ride directly on that fan shaft or kind of jack shaft. These some of the benefits of some arrangement 8s are, you can handle higher temperatures with these arrangements. You can handle you can handle corrosives because you have that motor away from the airstream. You can put a better shaft seal on there as well. An arrangement 4, you can see down below, is more compact. It's also less. There's less cost impact there, so you have a lower cost fan. You can use an arrangement 4, up to about 200 degrees Fahrenheit kind of standard. 100 degrees C or so is pretty typical. Beyond that, you have to start considering all the heat that's going to be generated and taken in that motor. The nice thing about these direct drive examples is, now with the common use of VFDs, they're a lot more flexible now. You can run these fans over speed, over the motor synchronous speed or below the synchronous speeds, as long as you take that into consideration in regards to motor safe speeds and fan safe speeds and the design of stuff. So they're a lot more flexible than they used to, because before you had to select these, at a motor synchronous speed, and you were kind of stuck there. But now with VFDs, there's a lot more flexibility. We see a lot more direct drive fans now than we do belt drive fans. It's kind of the trend. And when you can, ideally, if you make an arrangement 4 work for your application, that's certainly something you're going to want to explore, because it is cost efficient. And still gives you a nice bang for your buck. It has a small footprint, so there's certainly something to be said for. You see a lot of people trying to use as much arrangement 4 as many arrangement 4 fans as possible. So now we'll talk to the other side. We'll talk about the belt drives. So you see here we have an arrangement 1 in the upper right-hand corner, and we have an arrangement 9 fan. And the difference there is really arrangement 1, you have a kind of a unitary base or a floor mount motor. And then arrangement 9, you'll see the motor's actually mounted on the side of the bearing pedestal. So both of these fans are pretty, you obviously have a footprint impact between the two. And with the belt drive, you do have a lot of flexibility for running speeds. You don't have to be at that motor synchronous speed, and you can even be further from it than you could with typically a kind of a direct drive fan. These are also very good for applications where there's, arrangement 1 would be better for really high temperatures. Arrangement 9, you do have that motor kind of tight to that housing. So something to be considered if you have elevated temperatures over, 400 or 500 degrees, you certainly want to at least account for that, if not change to an arrangement 1 potentially. But with these, you do have a lot more components than a direct drive fan. You have belts and you have shivs, and you also have on the bearings, you're going to have some belt pull there. So that certainly can change the life of fans. So the arrangement 9 is a little bit more compact. You see that motor is mounted on that bearing pedestal. That does make for some difficulty sometimes when it comes to maintaining. If you do need to remove that motor, it can be a little awkward, especially when you get to large motors. Smaller motors, it's not a problem with, but it is just a different type of belt drive fan with a smaller footprint. Cost comparison wise, if you looked at bare fans, they're pretty similar. You have to add some accessories for the arrangement 1 fan with the unitary base and slide base, motor slide base. So they tend to be a little bit more expensive than arrangement 9s inherently. So some other considerations include fan noise. And with fan noise, it's just basically generated by turbulence through the fan housing. And this is going to vary with fan type and also flow rate, pressure, and fan efficiency. The more efficient your fan is, the quieter it typically is. These noise ratings can all be attained from the fan manufacturer. They're usually provided with your fan selection. So that way you can make sure if you do have a noise consideration to take into account, you can see how loud that fan is. And if it's louder than you expected, there's certainly measures via silencers and acoustic jackets and cladding that can be kind of taken into consideration to help abate that noise. Some of the physical limitations you're looking at is like inlet outlet configuration. Do you need an inlet box or an elbow? Are you kind of, it really kind of depends where your ductwork is coming from. Also, fan weight, if you're up on a mezzanine or up on a roof, that's certainly something you may want to take into consideration when selecting a fan. Also, ease of maintenance. Kind of talked about the ability to, for certain fan arrangements to help with maintenance. There's less parts, but also, if you need specific access to something that may be in a tight spot, you may want to make that known so the fan manufacturer can take that into account. Also, typically, the larger the fan or the slower speed you're running to meet a capacity, the more efficient it's going to be. And a larger fan running at 1800 versus a smaller fan running at 3600, that larger 1800 RPM fan may not fit into your space. So that's certainly something that needs to be known if that's a requirement, because a lot of times it seems like fans are kind of forgotten about, or we left this little envelope here for you guys, now you got to make it fit. So that's a common thing we see from applications. Also, a big one is flow control. How are you going to control control the flow and pressure of your fan? Most fans aren't just required to do one capacity. They may be turned down capacities or other requirements for the fan to be able to handle. And that can be done through various flow controls. Specifically, a large one is dampers. Those are directly mounted on the inlet or the outlet. And these are not compatible with all Airstreams. Something to be kind of cautious of is if there's corrosion or erosion, that's certainly something that can cause issues with dampers. And you can get special damper construction, but it's just something to note and be concerned of. The three types of dampers that are available for fan, you have an outlet damper, a variable inlet vane damper, and an inlet box damper. These dampers all impart a system effect to change the performance of the fan. So we're going to look at outlet dampers first. An outlet damper, basically it's mounted on the outlet of the fan. All you're doing is, as you're closing the blades from open to 90 degrees to closed, you're adding resistance to the system. And as you add resistance, you're going to change where that fan actually operates. And the couple options you have is a parallel or opposed blade. And a couple differences there. The parallel blade damper does not, it will bend air to one side of the duct for a little while. And it's also not as precise as an opposed blade damper. Opposed blade damper, a little bit more expensive. Air comes out a lot more uniformly, but it also is a much more linear curve when it comes to airflow. The change in airflow as you close the damper. A parallel blade is a little bit, at first, even though when you start to close it, it doesn't change much. And then it really drops off once you get to about halfway closed. So it's not a linear curve. So on the inlet side, you have a couple options, and you have a variable inlet vane damper, and a couple different, on the right-hand side, you'll see internal, which is mounted in the inlet cone or venturi. And then you also see an externally mounted damper. You can see through the internally mounted one, the upper damper on the right-hand side, that damper, you can see it has more leakage. It's not as inherently as robust. So it's not meant for, more difficult or demanding applications. But they do have the same effect. They both generate a vortex that pre-spins air into the fan, and that actually detunes the fan. It reduces flow, pressure, and your horsepower consumption. And these can be really good to kind of throttle back a fan if you don't need it to run, if you don't need the full capacity out of it. and also to help kind of change the curve shape. And we'll show a little bit more about that in a second. And the last type is you can actually mount basically what comes out to be a parallel blade damper on an inlet box. You'll see here on the right-hand side, you have the inlet box damper mounted here on top of the inlet box. And it does the same effect. It pre-spins the air into the fan, detuning the fan. And the last flow control is speed control. And this has obviously become a lot more common in the industry, that because of the flexibility of it and the power savings and you can get from this. So you can get a lot of energy consumption savings here. Controls the speed of the fan via changing the frequency that the motor actually sees. Motors do need to be designed to handle these. And in some cases with larger fans, we do actually make fan modifications as well to handle these. And basically, as you change the speed, you create a new fan curve. And, years 10, 20 years ago, we saw a small percentage of fans having these, and now it's basically commonplace. And in a lot of industries, it's basically it's required, for fans to come on VFDs, and that includes belt drives. And obviously direct drives come this way, but even belt drives we see on a lot of VFDs now, just for flexibility. So we kind of talked about how the fan curve changes. So with the outlet damper, when you have a fully open damper, as you close that damper, you actually ride back up the fan static pressure curve. So as we start to close it, you'll see that we're just adding pressure here and cutting our flow. Okay, so we're increasing pressure, and that's that added resistance the outlet damper is creating, and you're cutting down flow. So that's kind of the that's kind of how the outlet damper affects the fan. And you can see with horsepower, you don't have as large of effect because you're not changing the actual fan curve. You're staying at your same speed. That's constant. And you can see you're just getting a small horsepower savings here. So this is really just to add resistance as needed to help tune the fan for the application. You get more flexibility with an inlet vane or inlet box damper. You can see here. Here's our standard curve where the damper is completely open. And as you start to close it off, you start creating new fan curves, and you can see how the volume falls off, but your horsepower also falls off as well. So you're getting horsepower savings here. So that may help in certain situations when you don't require as much out of the fan. This gives you a lot of ability to turn down a fan. And one of the benefits of the inlet vane type damper or an inlet damper, you can maintain static pressure here. Okay. So you'll see with the VFD, you don't have the same static pressure capability. You don't lose as much of it with an inlet vane damper. So that's really good for situations where you need a 4 or 5 to 1 turn down. You're going to want to look at a inlet vane damper to help you control that fan. And the last one is speed control, your VFD. So as I mentioned, we changed the fan curve, and it's basically just mimics as you speed up or slow down the fan, it mimics the normal fan static pressure curve at 100%. And if you want to increase speed to 110%, it'll move back out here. And same thing if you go to 80 or 90%, it starts coming inside. And you see here we see these big horsepower savings when we're slowing down the fan. But as I mentioned, you do lose some of that static pressure capability of the fan at slower speeds. The most versatile fan really is a fan that's on a VFD with an inlet vane damper when it comes to turn downs. You can really get a lot out of a fan, and where you may be in an unstable portion of the curve normally, if you add that combination of the inlet vane and the VFD, you really get a lot of flexibility in what you can do, and make sure you stay at a stable point on the curve, depending on your application. It's so that's a good go-to in a demanding application with large turn downs, or they're looking for a wide variety of the ability to control the fan. So let's talk about some of the fan characteristics. We have centrifugal fans and we have axial fans. For the centrifugal, we see that we have some radial fans, a backward incline, and a forward curve. And the axial fan, we'll kind of look at a propeller fan, some tube axial, duct fans, and some vane axials. First, we have radial bladed fans. A couple characteristics here. The blade radiates out from the hub. We'll show a little bit better picture of that in the next slide. But you can see here is you have this very small outlet or very small inlet, and you have a small outlet relatively compared to the diameter of the wheel. You have options for cleaner, more high efficient wheels, and you also have options for wheels that can handle dirtier, high impact operations. The blade shape does resist material buildup due to the radial design. It's some people coin it kind of self-cleaning as it resists material sticking and clinging to it as it spins. Moderate to high static pressures here. Volumes can be relatively low on radial fans to kind of a medium volume. Volume wise, because of the small outlet, you can't go really high in volumes because you're going to have a really high outlet velocity. So you'll have losses, and you could have issues with, sending a large velocity of 8,000 feet or 9,000 feet a minute down the ductwork, which causes noise and can cause other concerns as well. So here's the radial blade fan performance curve. You can see here that with volume on the bottom, static pressure on the left, and brake horsepower on the right, you can see here that when we're at zero flow, we're at our peak pressure. So this allows this design inherently is stable from closed off with no flow all the way to wide open. But something to really consider here is this brake horsepower is ever increasing as your flow increases. So that's certainly something to know, because if you kind of overshoot your static pressure requirement, and let's say you sized it for 20 inches, but you only really need 15 inches, you're going to move, let's say 20 was here, you're going to move this, down to here on the curve where you only need 15, because that's where the fan's going to go based on the system curve. And your horsepower is going to drastically increase. That's an overloading brake horsepower characteristic, and just something to keep in mind when motors sizes are being selected for radial fans. We kind of talked about the blades extending radially out from the hub. You can see here in these pictures here, this is a paddle style wheel. This is one of the oldest designs of fan wheels. It's very blunt and tends to not be very efficient, but it is good for certain applications where you're handling material or handling some heavy dust loads, and they're also self-cleaning. It's hard for material to stick to the front sides of these blades as it's rotating. Efficiencies tend to be about 60%. Sometimes you can get a little bit better than that if you make a really good selection, but they're not efficient fans. They tend to be noisy. So something to take into consideration when you do need a straight radial wheel like this. Similar style wheel, it's basically the straight radial wheel with a couple rims on it, or front and back shrouds. So this wheel, you get a little bit more efficiency out of it because of the ability of the shrouds to generate some better efficiencies and higher static pressures out of that. So you'll see that, but you also lose some ability to handle material. Things can get stuck, hung up on the rims if you have stringy material. So it's certainly something. There's a trade-off there for that efficiency gain. You lose the material handling capability for any application. So when we look inside of a radial fan, you can look at kind of the relationship of the wheel to the fan housing. You can see that this wheel takes up almost all of the housing space, and that's for a few reasons. One is basically static efficiency. You don't have these dead areas where you lose efficiency and may have some recirculation. Also helps to maintain velocities coming in and out of the fan, so any material does not get stuck in the fan. And the last reason is to minimize any kind of buildup or hang up with material between the wheel or in that dead space of the fan. So this is very common in radial fans. You'll see that the wheel takes up a majority of the housing width. So this is still a radial style wheel. These are a little bit more efficient. You'll see that the blades still radiate out from the middle, but there is a curve to them and a little bit of a cup. These wheels are more efficient. than our kind of just the straight radial blade. You'll see that we have increased efficiencies from 65 to 70%. So we're already up 10 to 15% on that straight radial wheel. But the trade-off there is we have decreased material handling capability. And as we get more efficient, these fans are even quieter than your paddle style wheel. This wheel was developed in the 70s when there was some energy concerns. And obviously, as energy concerns have become more and more of these style wheels have been developed and continue to be developed for better efficiencies while still being able to handle dust loads. So this is really kind of a paddle style wheel here. It's a very heavy duty, rugged duty wheel. You'll see very thick blades, about 3/8 thick, 3/8 of an inch on these, with very heavy gusseting. This wheel rotates from this view in a counterclockwise direction. And this is for heavy material handling. If you're handling like wood chips, wood blocks, cans, we see even like aluminum slugs handled, or aluminum kind of trim. So certain wheels are kind of really developed for certain processes, and there's a trade-off there. Obviously, you lose a ton of efficiency, and they can be very, very loud. But there is their place for, they do have their place in the market, depending on the application. But for a clean air application, this isn't something you'd want to select. So that's why that's critical to kind of know what's being handled in the fan, and what really the airstream makeup is, so we can make that right selection. Another style of radial wheel is a pressure blower. So these wheels are a lot narrower than the kind of the normal style paddle wheel. These wheels generate high pressures and low volumes. So they're very narrow. You can see that there's a very small outlet, very small inlet and a small outlet. And that is to help with pressure generation. We don't handle as much air in these, so they're not designed for that. These are all for pressure. You can see that the inlet and outlet is very small compared to the diameter of the actual wheel. Typically, we're not looking to handle material with these. That's not really what they're designed for. You see them in a lot of combustion air applications, some pneumatic conveying. So we're looking at pressures up to about 120 inches here, with what we would call a pressure blower. Here's kind of showing those wheels and for the pressure blower. And you can see, again, we have a little bit different design, but it is still coming out radially from the hub. These do have a little bit of a cant to them. And this wheel actually rotates in the counterclockwise direction from our view. And this is the top wheel is actually aluminum riveted construction. So that's specifically used for clean air applications. The aluminum can't handle a lot of temperature, and it cannot handle any material. So it's a lightweight, lower cost, but still, because of the weight advantage, you can certainly handle higher speeds, provided that that application has clean air. Down below, you do have a steel wheel, so you do have some flexibility, but that wheel is also not as efficient as the aluminum wheel. So you do kind of have a trade-off there. Again, you can handle a little bit more, some light dust or some dirtier material, but at the same time, you have that trade-off with efficiency. And these wheels, you can see how narrow they are with long blades, and that's because we're looking to generate pressure and while moving lower volumes. That takes us back into the backward incline fans. So you can see here you have a large inlet and a large outlet. These fans move higher volumes, lower pressures. They tend to have higher efficiencies, up to, depending on the wheel, 70, 80, even 85% efficiency. And the blade shape on these, though, is conducive to material buildup. So it's certainly something to take into consideration, is that we don't want to handle a ton of material in here through these fans. Show some characteristics of the fan curves. So here's our fan static curve. So again, you kind of have this zone up here that we don't want to operate. You have your peak pressure. So really, you're going to be typically operating your curve here for these types of fans on a backward incline, because we're unstable up in this region, because any variation in pressure is a large swing in flow. And then you'll see here a key characteristic is the brake horsepower curve. If you select a motor over this brake horsepower, at this specific speed, you can't ever exceed, no matter where you're at on the fan curve, you can't exceed that brake horsepower. So it's something it's a nice feature versus the radial fan where you can exceed it's linearly increasing, and it just kind of goes up with flow. So this has a cap on it at a specific speed. Show you kind of the wheel design here. This is a single thickness blade. You'll see we have one single blade here. It's a kind of a backward cant on it. And as this rotates, we actually rotate this again in the counterclockwise direction. You'll see some reinforcements here for just for support and to restrict any deflection in the blade. And you can see a large inlet, and we talked about our large ID on the inlet side of the wheel, and talked about how much flow these handle versus pressure. And you can see they're much more efficient. You're up to 80%, and again, not for handling heavier materials. So now we go even to a different backward incline design, and that's the airfoil. The airfoil is shaped much like an airplane wing. You can kind of see here is kind of a good example. You can see the two, the top skin and the bottom skin, using the weld stains there. So this is a very efficient build, but it's also very sensitive to any corrosion, moisture buildup, or erosion. You really want to have this in a clean, dry airstream. These are, some of the most efficient fans you will find. And with that efficiency also comes some some better noise characteristics versus a radial or even the single thickness blade. Here's kind of the downfall of an airfoil blade. You can see here at the blade nose, we have erosion where it's actually eroded the blade tip. The blade nose away, and you're going to have further erosion. You're going to build up material in there, and then you start having balance problems. It's eventually going to lead to failure. So the trade-off there is the airstream with an airfoil needs to be as clean as possible to make the proper selection for that. Otherwise, you can have issues. You also see forward curve fans, and with the forward curve fan, you'll see that you have a wheel here that has many blades, cups air, and it's very, relatively for the size, they move high volumes at a very low static pressure. You see these in a lot of HVAC furnaces, replacement air applications, and they do tend to run at slower speeds. They're just not inherently designed to run high speeds. It's also called, a squirrel cage in a lot of applications or different industries. As you can see, a lot of the blades are riveted. You do see welded construction on larger ones, but they are delicate, can't handle material. So that's kind of the offset there is, for the kind of the price point and the application, they're much lighter duty. You kind of see here some characteristics of forward curve fan curve. You can see here you have this region of instability just left of the peak static capability of the fan. So you're going to want to be operating this in this section. When you get to axial fans, these tend to have compact designs, usually obviously duct mount fans, or you'll see them for exhausting up on roofs, or even bringing air in into buildings from the roof. Usually high flow, low pressure application. The air flows straight through the fan. We don't actually bend it like we do with a centrifugal fan. A couple of those different fans, you have a propeller fan. This is used for a lot of replacement air applications, just general ventilation, typically no ductworks attached. Again, with kind of following the axial fan, it's a high volume at a very low static pressure. Any kind of differences in static pressure can certainly reduce the volume because these only produce a couple inches of pressure. So you'll see here that we also have the duct and tube axial fan. In these fans, you'll see you kind of have a generic blade. It's more of a propeller style blade, lower cost than some of the other axial types with a vane axial. You don't see any straightening vanes. Again, low to moderate static pressures. We're only looking at a couple inches, and a lot of applications for these are spray painting or fume exhaust systems and general ventilation. The last axial fan you run into is a van axial fan. And with the vane axial fan, you actually have an airfoil blade, that's on a hub, and that's either a fixed pitch or an adjustable pitch hub. There's straightening vanes in these fans to help in pressure capability, but also fan efficiency. The picture on the right, the upper right here, this is actually a fixed pitch. So these are cast blades welded to a cast hub in a fixed orientation. And then down below, you actually have an adjustable pitch. And these are cast blades again, but there's a pocket here. And these can actually be changed in the field at rest. So when the fan stopped, if you need to tweak, the performance because you may not be on a VFD, or if it's a site that doesn't allow for a VFD, there's certainly some flexibility here to change the performance of the fan as you change that blade angle. So a couple notes, just when you're talking about fan selection to actual conditions, we've got to remember that performance is affected by any changes in gas density. If there's any changes in temperature, moisture, elevation, some of the other things, corrections must be performed. All rating tables from fan manufacturers are published based on standard conditions. So that's where fan selection really kind of comes into helping you, because you can, the fan selection process can take that non-standard condition into account versus what you see in a bulletin or off of a cut sheet. Also, when you have when it's cold out, or if you do have a hot application at ambient temperatures, when you're starting up that fan, there's some considerations to take into account that you just want to remember. And that if the density is significantly lower during these cold periods, you need to make sure the motor can handle it. And ways of kind of dealing with that is you can put it on a VFD or even a damper to choke back that fan while it's going through startup. And of course, if we're in cold conditions, as most of us are, winter conditions definitely decrease the air density, and that can cause an increase of horsepower. So it's certainly something to consider, is that, what's your worst condition if your fan's outside? If you're -40, you're certainly going to want to account for that via either some motor changes or some motor considerations, or being able to choke back that with a damper or on a VFD to kind of overcome that. So once you kind of have taken all those considerations into account, you can go to your fan selection program, and the fan manufacturer will put some parameters into the program, and kind of knowing what application you're looking for, they're going to start making passes at selection. In this case, we put in a few parameters, and then from that, you'll get some various selections typically. You can see here there's a bunch of different options, and they can kind of start to hone in on what's exactly the best selection for your application. Are you really concerned about efficiency? That's something they can target. Or are we really concerned about sound? That's certainly something we can take into consideration to make sure that the best fan is selected for your application. And once you kind of make that actual selection, you actually get a fan curve. And the nice thing about this curve is, if you do have a special density or non-standard air, this curve takes that into consideration versus what you see in a bulletin. And most fan manufacturers, have software or online programs to be able to help you with your fan selection. You kind of see your fan curve, and it gives you a lot of details about, what the efficiency of the fan, and your outlet velocity, some of the other details you'll need for to know for your system. So we'll shift gears a little bit here. We'll talk about fan maintenance. And I guess the biggest overall thing with fan maintenance is really having a schedule and kind of sticking to that schedule. And if you can, to kind of audit the fans, if it's not a new fan and it's been in service, it's always good to get out there and kind of get a baseline reading. So you have, so you can compare that baseline reading to kind of how the fan is trending in the future. So it's always good to really do, inspections when you do have the opportunities in a maintenance window or a shutdown, or if you're doing some other work on the fan, take advantage of that and kind of get a baseline. So most fan manufacturers and or a lot of companies have their own service checklists and maintenance lists. So It's really important to kind of have that as a baseline, and really it's a nice tool to kind of follow along to make sure you don't miss anything, or kind of taking everything into consideration when you're first looking at a fan. And in that checklist, that includes wheel inspection. Is the wheel clean? Does it need to be cleaned more often? So that's certainly there's certainly a lot of little things in there that you can make sure that you account for, and you make sure you're watching, so you can kind of help maintain the longevity of the fan, and hopefully live out its service life. So when we talk about lubrication, there's a lot of people say there's no such thing as too much of a good thing, but you can see over lubrication is actually a really big issue with fans. If you over lubricate it, it's certainly become a heat issue, and also housekeeping issue, and it can lead to bearing failure. So it's really critical to kind of make sure your lubrication schedule is correct and you're lubricating the fan properly. So you can see on the photos on the left-hand side, we have over lubrication issues. And when you lubricate a fan, that first lubrication, when you inject that new lube, that new grease in there, the bearing actually heats up a little bit, and it'll start to dissipate heat as that grease breaks in. So that's something you want to watch as well, is if it's retaining heat, then you might want to start looking for some other problems. On the flip side of that, under lubrication is obviously an issue as well. And you can see there's a fan example here that burned up some bearings due to lack of lubrication. So you really kind of want to find that happy medium when it comes to lubrication. And a good way to do that is obviously use some of the fan manufacturers' installation and maintenance manual is a good tool, but also bearing manufacturers have their own as well. And so do motor manufacturers. Most fans use a lithium complex grease, so that's something you definitely want to be aware of. Most motors actually use a polyurea grease. Those two greases are not compatible with each other. So it's something you certainly want to make a point of and a note of. And you can look on, fan nameplates and fan lubrication guides that's on the fan. And, it tells you that, to use a lithium complex, usually a grade 2 grease. Same thing for motor nameplates. They tell you what kind of grease to use. So just make sure that everybody realizes that those are not compatible typically, or those are not compatible, as most motors use a polyurea based grease. And again, following the fan manufacturer, the motor manufacturer's guidelines is certainly going to help your fan, be serviceable for as long as, we see fans go all the way to, 40, 50 years. Design life's typically kind of centered around 20 years. Obviously there's different applications, but certainly lubrication is a really big part of fan longevity and fan maintenance. So when we talk about bearing temperature, that's certainly something that you want to kind of have a guideline. Most fans you see kind of run between 140 to 160 degree Fahrenheit. That's about 40 degrees C to 55, 60 degrees C. And that's kind of normal. And we kind of have some guidelines about anything below 180, even slightly above that is pretty normal. Once you kind of start to see it creep up to near 200 degrees, or about 100 degrees C, you're really going to want to kind of start to investigate, and you likely have a shutdown alarm about 225 degrees to kind of figure out what's going on. And like I said, when you do first grease a bearing, it will run a little hotter. So you may want to watch temperatures after, if you're concerned about it, or if it is running hot, make sure it just starts trending down and kind of normalizes again after re-greasing. And like I said, anything above 225 degrees, you really want to shut it down and kind of look and see if you can identify the problem. A couple ways to measure temperature in fan bearings or in motor bearings. You do have thermocouples and RTDs. And here's an example on the right-hand side of a bearing RTD, and that instrument actually, is bedded inside there's a little probe bedded inside the bearing near the outer race, and that helps monitor the temperatures of the internal temperatures of the bearings. You can also use infrared thermometers, but realize that you're only looking at the external temperature at that point. So there is some offset there. We see about 10 to 20 degrees kind of difference between external temperature and internal kind of bearing temperature. So something to consider. Not all applications have RTDs or need them, but a thermometer can also, infrared thermometer can also help you monitor the temperatures that the fan and motor bearings are seeing. So when you look at V-belts, a couple things really kind of come out when you're looking at an inspection. You want to look for any wear, any cracking. Is there any kind of debris where, in the belt guard or below where the belt is starting to deteriorate? Also, any excessive noise. Often at startup, you may hear a little squeal. As long as that squeal goes away, typically it's okay. It's just there's some belt slip when you're first starting, the motor across the line, and it may squeal for a second, a couple seconds. As long as that goes away, it's typically not an issue. Other big consideration in V-belts are tension and alignment. So we talk about belt tension. This is critical to help maintain longevity of belts. You don't want your belts too loose or too tight. This is kind of back to the lubrication. You kind of want to find the right spot. Any belt selection is given with a tension required. It gives you a deflection value and a force value. And one way to kind of measure that is a tension pen or gauge. And that's just that's a nice tool to be able to measure belt tension, make sure you're in the kind of the right range. And also, you see a lot of people will use their fingers as a tension gauge, and that's really not the best approach because your finger's not calibrated, and so the tension pen or gauge is relatively inexpensive, an easy tool to carry. So when you are looking at V-belts, that's certainly something that you want to check to maintain that longevity, so your belts aren't slipping or they're not overly tensioned, causing further issues with both belt breakage and also you have a force pulling on your bearing there. So that can certainly cause issues with your motor or your fan bearings as well. Another way to actually, a newer way that we've seen a little bit more frequently is a sonic tensioner, and that's using frequency. Any belt has kind of a natural frequency, and based on that, you can get some for that belt. They actually have the frequency range for the proper tension based on that you can get from the belt vendor and on belt selections. So a sonic tensioner is another way to do it and to measure belt tension. Talk about fan alignment and how critical that is. You see on the left-hand side, you kind of have coupling alignment. You see typically laser aligning tools used for this. You want to make sure that there's, you're not exceeding the manufacturer's recommendations of any angular offset or parallel offset in your coupling. So you want to make sure that's intolerance, so you get the best life out of your coupling, but it also doesn't lead to any vibration issues or in the fan or motor itself. And then on the right-hand side, you see shiv alignment. You see another laser type tool used for shiv alignment. This is nice because you can use this. You can use this by yourself. You don't need an extra set of hands, but not everybody has a laser alignment tool. And this is good to make sure that you get the best longevity out of your belts. And if you don't have a laser alignment tool, you can still kind of use old techniques. A lot of people use a string, and this is kind of an example of the string on the bottom here. And you may need an extra set of hands for some of these, especially with a straight edge if you have long belt centers. But there are other ways to kind of look at shiv alignment without having a laser. So these are okay practices. Obviously, the best would be a laser typically, but there are other ways of kind of making sure shiv alignment looks good, so you get the best longevity out of your belts, and you're also not kind of putting the wrong kind of forces on your motor shaft or your fan shaft. So the last kind of main fan maintenance thing we'll talk about is vibration. Vibration is really critical in fans, much like lubrication. Typically you kind of see vibration measured in the vertical and horizontal on fans, kind of from manufacturers. You do see some actual axial measurement. That's typically a little bit more of an aerodynamic plane, a little less predictable. It kind of depends on what's going on in the inlet and what the pressures are. But vertical and horizontal planes on the bearings are your typical measuring points. And vibration is really critical, and you want to make sure your fan's kind of in tolerance for your application, so you get the best longevity out of it. Because vibration can lead to all sorts of problems, including bearing failure. It can lead to wheel failure, and other other issues and damage to your equipment. So it's really good to kind of have a baseline reading once that fan's installed, after it comes balanced from the manufacturer, just to make sure it's where you want it. It doesn't need to be further balanced due to the install. Some ways to kind of monitor vibration. You see a vibration switch down here that will attach directly to the fan bearing. Kind of show some, you see some accelerometers here in this picture. And so this is the horizontal direction. This one's actually in the axial direction. You see it's axially parallel to the shaft. So here's a couple transducers here to help monitor vibration. And that's really nice because it goes back to your PLC. You can trend data, so you can kind of watch. It really helps with the overall machinery health and kind of the equipment. And if you see any trends or anything, you can certainly investigate or shut down the equipment and look at it further and see if it needs some maintenance to kind of maintain longevity, so you don't have any catastrophic failures. So certainly good tools. And you can also use a vibration pen. Not all fans are set up for vibration monitoring, but you can certainly use a vibration pen and go around and put that on vertically or horizontally on the bearings to help you monitor that, so you can still take readings, even though you may not be sending signals back to a PLC or collecting data. But you can certainly trend data still and grab some instant readings to make sure your machinery health is overall is good. So when we talk about kind of the vibration levels, there's a couple points we kind of want to make. This table's from AMCA 204, the vibration and balance quality standard. And a couple things is, typically when you see different mountings, you'll see a rigid mount where you're basically kind of anchored to concrete or something like that. And then you see flexibly mounted where you're up on, isolators such as spring or like a rubber in shear, or even a vibration pad. So those numbers differ. You'll see the rigidly mounted numbers are lower than the flexibly mounted motor, because you're inherently gonna, the fan's gonna move a little bit more. And you'll see different conditions here with startup, alarm, and shutdown. And typically in the fan industry, both industrial and commercial, you kind of see BV3, BV4 as being the typical fan application categories. So that's, tell the fan manufacturer, I want this fan at BV3 or BV4. And that way it leaves the factory at that level. And then out in the field, you should see similar levels. And this is kind of the data you can see. First, you have millimeters per second, and then you have inches per second. And you can see it's, you have a startup level of 0.25, an alarm level of 0.4, and then a shutdown level of 0.5. So certainly something to take into consideration. Also, make sure you know how you're measuring it. Are you measuring it as a peak value, or are you measuring it as an RMS value? Because you see these numbers vary differently. So you just want to make sure you're using you're comparing it to the right column based upon how you're actually measuring that vibration level. Couple documents that are kind of nice for troubleshooting, and they do have some maintenance things outside of just a fan maintenance IM manual, is AMCA publication 202 and troubleshooting. It does have some kind of various diagnoses for depending on what you're seeing. If you're having poor performance or if you're having seeing vibration issues, it does have some of those some of that information as well. So it's a nice piece of literature to kind of help you and aid in your overall fan maintenance, and might be a good reference. That kind of wraps up fan maintenance and my section of this presentation. I want to thank everybody for joining me today, and I'll turn this back over to Lisa.
Okay. Thanks so much, Mike. I appreciate it. And also, I want to thank the audience for their participation today. We can get to some Q&A real quick for anyone who has the ability to stick around if they don't have to jump off right this minute at the top of the hour. So, Mike, can you do me a favor and unshare your screen? Thank you. And then I am going to reshare my screen. All right. So, a couple quick notes. As Mike mentioned, here are some resources that you can certainly use if you'd like more information on the topic for today. And again, thank you for your time. For PDH credit, those will be issued within 30 days. And please remember to complete the survey that you will receive within 1 hour. I do want to make note of our next session. There was in your emails notation of a date and a time change. The session that we will have next is going to be on Tuesday of next week from 2 to 3 p.m. Eastern Time. The topic is fan system effect and system effect troubleshooting. The presenter is Dave Maletich, who is the Vice President of Marketing at New York Blower, a colleague of Mike's. So that will be a great session to follow up with what we talked about today. So, with that, I would like to see if anybody has any questions. And I'm going to pop on camera here if technology will work to my advantage. I know that I submitted a question, but that is not the most critical part of today. All right. Well, while my camera is trying to get warmed up, we do have a question, Mike, and it is, what should you do if you mix lithium and polyurethane greases in your fan bearings?
So it's going to depend on your fan bearing type. Certainly, you want to flush it out as best as you can. If you have a pillow block where it's not accessible, like a split pillow block, you definitely want to flush as much of that grease out as possible. And I'd certainly monitor the health of that as you after you flush it out and refill it with some lithium grease. The worst case is you replace the bearings. But if you do have a split pillow block where you can take off the cap, you can certainly scoop all that out and clean that out even better. But I would go either to purge the bearings as best as possible, or obviously worst case scenario replace. And with a split, you can certainly scoop all that out and kind of repack the bearing and just continue to monitor it after you make those changes.
Okay. Awesome. So the question that I had put into the Q&A was, would you recommend auto lubrication units for easier maintenance?
So typically we don't really, typically you won't see most fan manufacturers kind of recommend that. That's certainly more of a kind of a customer decision. Most customers will kind of lead you down that path. We do provide auto lubers. Plenty of fan manufacturers do provide them. They are good for a lot of things. It is nice to see it delivers a much more consistent amount of grease more frequently versus kind of injecting a ton of grease into it. And so you don't kind of have those heat up problems. So it is good for that. Some of the drawbacks we see with them is we're very concerned about people just kind of set it and forget it, and they don't come back to that fan for 6 months when that cartridge needs to be changed out for those auto loopers. So certainly can be a really good tool, but it just needs to be kind of made sure that you don't kind of just set it and forget about the fan and come back.
Mhm.
I need to replace that cartridge in 6 months. You want to continue monitoring that fan, but it does provide a really nice consistent grease injection, and also kind of that smaller quantity versus dumping a ton of grease in there after let's say 2 or 3 months. It'll do smaller quantities as needed, and you can set that, which is it's kind of some nice flexibility to have.
Sure. And I did mention to the audience members in the chat, if you do have questions that you would like to submit, and if we don't have time to get to them, we will follow up with you with the answers via email. So don't hesitate to ask your questions just because you're looking at the clock. And of course, if you do have questions, you can send them to Sarah or to myself, and we'll get you a response. So, one last question for today, Mike. Are there any drawbacks of using VFD on a fan?
So when using a VFD, as long as the fan is designed for it, and that comes with the motor being designed correctly. If you do need some kind of shaft grounding device, there's really not a ton of drawbacks. You do have some concerns though. VFDs can be operated from 0 all the way to their synchronous speeds. So throughout that speed range, you may see some natural frequencies that's just basically a frequency of the actual installation. And if you see a frequency with some large spikes where it may, there's some energy there, and it may be a point that could cause some fan damage because of that excited state, that vibration, you're going to want to make sure you kind of lock out those ranges. To make sure that you don't operate in that range consistently. You can go through that range as you speed up, but you don't want to kind of stay there, especially if it's at a very excited state where vibration is dramatically increased and it can cause damage to the fan. So just some considerations really need to be taken into account. Not so much that there's a ton of drawbacks, and you want to make sure that you're taking care of any stray currents for the motor and also through the fan to make sure you don't do any damage to bearings or other systems.
Awesome. Good info to have. So I know we're a few minutes over the hour. I do want to thank you, Mike, for your time and your expertise today. This was a session just chock full of lots of good info. As we mentioned at the beginning, the recording and the PDF of the presentation will be available on the Odell website within 48 hours. If you do have follow-up questions, please send them to Sarah Johnson or to myself, Lisa Cherney at AMCA. And we look forward to having you all join us on Tuesday at 2 p.m. Eastern Time for Fan System Effect. We'll see if Dave can outdo Mike. They can have a little in-office rivalry there. So, Mike, thank you again so much, and thanks to the Odell people for joining us in this session today.
Thanks again, and have a great day.
Yeah, you guys too. Everybody have a good day. We'll see you soon.